embedding that I can call J, which goes from the whole mathematical universe, which is basically all the sets, to itself in the end. But it moves in a non-trivial way. It is non-trivial. And this is yes, and this is the way that I try to model, or this is an analogy, a mathematical analogy for the generative implicate order. What happens is that so this part you could see as this in a way, where you move, where you have first you have the unfoldment process. You can also split this split J into two parts if you want to, and then see this first part as an it is an elementary embedding. Oh, sorry, I didn't mention what an elementary embedding is. An elementary embedding is basically something that preserves everything that can be defined mathematically. All relations, everything is preserved. That's all it does. And what I'm saying is, I'm assuming that it exists, and I'm assuming that it's non-trivial, so that it actually does something, so that at least some set here is moved to another set.
Do there exist non-elementary embeddings? So does an elementary embedding preserve non-elementary embeddings?
Yes, if you can define it mathematically, yes. Non-elementary embedding. What would you mean? Yes, yes.
Yeah,
well,
I
any
mean,
embedding.
I was asking. That was the first question. What is a non-elementary embedding?
Oh, a non-elementary embedding.
Yeah.
Well, it would be something. I'm not sure. You mean the opposite of somehow? I don't know.
Well,
just a function? Any function? Yes, it preserves
because
all
I'm just checking the definition, because the definition is a bit vague for me. So
yes.
if there are non-elementary embeddings, I suppose so, then an elementary embedding also preserves the non-elementary embeddings.
Yes, it does.
What does that mean?
Well, it means, for instance, what could be a non-elementary embedding? This is what I'm not sure about, but say it's just a function. Does it preserve it? Yes, so if for any formula, so if you have some formula...
So it preserves every function that is not an elementary,
yeah.
Any definable formula?
Yeah, yes, and yes, mathematically definable formula. If you have any mathematically definable formula that holds true in the domain, then also this will hold true. It will also hold true. So yes. So this is just a way of modeling this. Is it okay? So I can do it perhaps this way, and there many things can be said about it. But is it interesting, really? Can it be related to physics in some way? What can we do with it? I would like to. Well, is it interesting? Yes, I think it is, because the idea here is that we start with this dynamics, and what we're going to do is that we're not going to add anything new to it, but we're going to let it act on itself. So, can J act on itself? Can we apply J to J? It turns out that it's possible. So we can define application, and when we have J acting on itself, this will generate so we will have many different. We can look at all possible combinations of it. So we have J acting on J acting on JJ, and so on. So what we turn out to have is a universal algebra, which is just a set with an operation, and the operation is an operation of application. And what are we really interested in if we're interested in physics? Well, we're actually interested in going from the explicate to the explicate in a way. This is the description that we would like to have. Although this might somehow be fundamental, we're still interested in describing the evolution of processes where we first measure something and then let it develop and perhaps measure it at a later point. So you could see that. So this is, I think, it was Nick who had this and stressed that this is what we want to try to model in a way, and this is where our implicate orders would be. We're going from the explicate through the implicate to the explicate, and so we can, in order to see how the explicate orders are related to each other, we can look at AJ, this universal algebra. So, what is it like? What do we know about? What can we know about it? Well, it turns out that this algebra is left distributive. And so, for left distributive, so if A, B, and C are elements in AJ, this is what we have. Left distributivity. It's not right distributive, and this is the only thing that we have. There are no other. It's not. Yeah. Mm-hmm. So okay. So this is a left distributive universal algebra, and this left distributivity can now help us to see how the different processes, if you like, are related to each other. And this is where we can learn how we go from one explicate order to another. It also turns out that one can define linear orderings on these elements, and there are different types actually. But yes. So that is something else that is perhaps interesting in it. And also application. Application is different from composition. So and it turns out that okay, I wrote it down here. Application. If we look at everything that is reversible, just at the reversible part of application, in a way. So we say I and K are elements in this algebra. Then we have this relation, and this. I don't know if you I took it away if you remember, but this is very reminiscent of something that we've already seen. Namely, from this, if we see this as explicate orders and the unfoldment and enfoldments, from this we can derive then the Schrödinger evolution, if you like.
But the only elements in your algebra are applications of J to itself?
Yes.
So the I and the K are applications of J to